now we will go over to our next presentation. Jamie, welcome to Func Prog Sweden.
Hello. Thank you for having me. Hope you can hear me well.
We hear you well.
Okay, good. Um, yeah, so I should share the screen now then, I guess. Okay. Yeah, so my name's Jamie. I work at this Scalacenter, which is this free basically a non-profit that supports the Scala language. And I want to talk to you today about how in the basically how the standard ecosystem tools that a developer gets, how does that improve the speed of Scala builds? And if you, let's see, yeah. So just a little taste of Scala. It is a programming language in the sort of functional space. It runs on Java Virtual Machine, but we also have a JavaScript runtime and a native runtime that's based on LLVM. And this is kind of an example of some code that uses purely functional effects to describe a web server that, I don't know, has two concurrent ways to fetch the weather that it raises. And here's a sort of another example where we have some simple data structure. This demonstrates the metaprogramming capabilities of Scala because we declare this pet structure derives the codec type class, and that allows us to generate some JSON. The point being is that Scala has a lot of machinery inside of it, inside the compiler, including over 100 separate phases of transformation that it goes through from the source code into the final products of the program. These 100 phases are fused together, so it mainly is only about 10 actual traversals of the tree. But anyway, moving on. I would like to talk to you about just an overview of how do we build Scala projects, and then what are the steps that the build tools take so that it doesn't take so long every single time you build the code, or even how to optimize building the project from the first time you ever try to build it. And if you are used to using Scala, then I'll have some tips of how you can arrange your projects so that they can take advantage of the CPU to build more efficiently. So, like I said, I work for the Scalacenter. We are a non-profit organization based at EPFL, which is a federal university in Switzerland. And we support the open source ecosystem for Scala and also provide free educational materials. We also sort of manage the community, acting as a sort of bridge between industry players such as Disney streaming. So that includes yeah, Disney Plus, I guess. And then there's some other names like Lego or Spotify. There are some companies that use Scala. And then we have, you know, over 1 million separate sort of projects that exist in the open source ecosystem that have been uploaded. So there's a lot of activity in the open source that we're trying to improve. And basically we try and improve the life of developers by making their tools faster and easier to use. And this is our team. We're very small. And we are funded by donations. So we are currently looking for more industrial partners. So I don't know if you like using Scala, consider talking to your employer if you work for a company about the Scalacenter, what can be done there. Anyway, so the main agenda, I'm going to say, let's talk about how we build a Scala project. And as a sort of heads up, I will be talking about optimization. So just bear in mind that all machines are different, and it's not good to hyper focus on specific ways you can optimize a build just because what works on your machine might not work on someone else's machine, etc. So let's dive in. Let's imagine that you have a sort of simple web server. It's basically a small module with about 50 files and a few library dependencies. And yeah, it's going to take some time to compile. This is a typical way you'd build that program. You run Scala, run web service, and then what's going to happen when you click this command? You're going to see this compiling project, which is basically just a one-time job where we start fetching dependencies and we might run some source generators. For example, if you use protobuf, maybe you want to generate some code from a schema. This is only going to happen one time every time you sort of change the configuration of your project. So this is almost like a free amortized cost. If you don't keep changing your project, then this only happens once. Then we get to the real meat or the body of what's going on, is that we're actually compiling the code. And this is the slowest part of everything because, you know, building code is something that happens every time. When you make a change, you have to rebuild the code. So we want this to be as fast as possible. And then, yeah, when you finally build the code, then you basically make a little wrapper, which on Java is pretty cheap because you just tell the JVM to run your class files. And that is a cheap operation. So that is happening, again, every time you build the code, but it's very fast. So let's focus on this step, which is compiling the project. Let's say the first time you build those 50 files is taking, you know, like 15 seconds if it's a really big project. And every single time you, for example, change one line in your code just to do a debug statement, print debugging, we'll have it. You wouldn't want it to take another 15 seconds to build over and over again, especially when you then delete your debug because you found out what was the problem. So, you know, this is adding up to a lot of time when really you want to be going quickly as possible, doing a fast change, iterating, etc. And luckily, because we actually have this in the Scala ecosystem, and that is thanks to incremental compilation. And if you don't know what that is, basically it's a mode of compilation where we can say that given that we've already compiled something at least once, then we can compare any changes that you might make in your code and only recompile those changes. And hopefully that ends up taking less time than cleaning the whole building from scratch. Yeah. Let's give a little diagram of what's going on. So I have a bunch of Scala files. And instead of compiling all of those, we're going to say, actually, you only edited this one file. So we'll recompile that. And then when we compile that file, we can then track the changes in the APIs that the other files actually use. So then we say, oh, you know, because you changed A, you changed the definition of one of those things, then that means that F and D might actually not compile anymore. So we need to recompile those because they use some definition from it. And then let's say we're done in this case. And as you see, we've only recompiled 3 files instead of all those others. So the goal is that hopefully this should be faster. But this is a very vague, wishy-washy, not very concrete definition. So we do have some metrics that we can use to judge if the incremental compilation algorithm is really succeeding. And those 2 golden rules, let's say, are that it has to be correct. So that means that everything that must be compiled is compiled. We cannot be left in a state where, you know, you actually start running your program, but then it breaks because now the definitions don't properly link at runtime. And then the second thing is that, well, we are making sure that we're compiling less than before. So we should really check ourselves that is this really actually faster than just compiling everything? So there's two sort of metrics like that. One is how long does it take to recompute the dependencies and perform a plan of what should be compiled and when. So we really need an efficient invalidation, and we don't want to compile too much. So that plan shouldn't include anything that isn't necessary, so that we don't recompile more than is necessary. And in the Scala ecosystem, we have a tool called Zinc, which is, it's an incremental compiler for the Scala language. And it maximizes those two goals that I laid out before, correctness and performance. And it uses this thing called the name hashing algorithm. And I'm going to outline how that works for you right now. So here's a little diagram. So in Scala, there's many different build tools you can use. There's Maven, which no one uses. There's SBT. A lot of people use that. That's like 98% of Scala users use that. And there's a couple of others. But essentially, when you, even if you edit one small file, that basically ends up, and you tell the build tool to compile, like it doesn't necessarily know what actually needs to compile. So it's going to tell Zinc, which wraps the compiler, please compile every file in the project. There's going to be 50 files. Then it's up to Zinc to decide what it should do next. And let's say it's the very first time that we've ever seen these files. So Zinc hasn't seen these files, so it says we don't have a cache. So we're actually going to compile all those 50 files. And so we shove those 50 files into the compiler, and we add the library dependencies to what's called the class path, which is basically the list of libraries that have been previously compiled. So that might be things you downloaded from the internet. In Scala, we build basically from compiled artifacts. We don't do source dependencies like some other languages. So inside this jar, we'll basically have class files and tasty files. These are the final products of the compiler, not source files. So once we compile all those 50 files, then we're going to get those class files into this class path, which is like this cloud thing in the corner. And Zinc will produce this analysis data structure, which is basically is stored on the file system. It's this cache, so that even if you shut down the computer and reboot it the next day, that cache will still exist. Then, once it's produced that one time, there's one run of compilation, then we're going to say the build is finished. And then let's say you edit one file again and tell the build tool to run. Then it's again going to say, oh yeah, compile everything to Zinc. But now Zinc knows, because it has that analysis, that it can compare the source files with this analysis and say, actually, some bytes in the A file changed, so we're only going to compile that one file. And then the way this works is that we can reuse the products of the previous compilation, which is this cloud down in the corner. So those are all the files that were compiled before, and then Scala knows how to read those so that we can basically only process one file. And then we're going to produce a newer version of this A class and update the analysis with the changes in its API. And then this is still in the same build command. So after we built that one A file, then Zinc checks inside its analysis and says, oh, right, actually, these files D and F, they use some definitions that changed in the A Scala file. So we need to double check that the program's still safe and correct. So we should recompile those D and F files. And in the same process as before, we reuse the previous compilation, feed it in, and we compile those two files, and we can update the analysis. And then Zinc will compare the analysis again, say, actually, there's nothing else to do. So then we go back to the build tool and say our build command is done. So hopefully this step where we actually did 2 runs of compilation, first A and then D and F. Yeah, the goal is that should be faster than compiling everything. So in order to help you take advantage of this incremental building algorithm, it's quite useful to actually use small files, because if you put everything into one huge file, then that's a lot of work for the compiler, because there's nothing for it to granularly attach to. It has to, the only input it knows is single files. So just whatever line you change, even if you make 1 character change, it's going to have to process all that code again. So it's really useful for you to split up your code just for even, good practices, just so that you can understand the code base. It's good to split up your code anyway, but it actually has a benefit to building your code, because the more small files you have, then the less inputs need to go into the compiler, and it means that you have a more fine-grained graph of dependencies, such that, yeah, if you only change one little definition in one small file, and perhaps it's only used by another small file over here, then that's a lot less work. So it's a good idea to use smaller files. So now let's have a look at this analysis jar. And this is going to be this is the cache that's on the file system that Zinc uses to judge what should be recompiled. And it's basically made of 3 components. There's stamps. So think of that like timestamps. And it also records the hash of the structure of a file. So it's it doesn't know anything about the structure of a Scala program. It just knows the bytes. It's just a cache of like what bytes were in this file. In a very efficient way. It's just a small string, like a hash code. Then there's a separate structure which is more complicated, which is the APIs, and that stores the signatures, the public signatures of every definition in the entire program, in the entire class path. So yeah, it's a more simplified form than the real Scala type system, but it's enough to basically track what things are necessary to recompile. Then the final structure is dependencies. And that basically says like this file depends on this name that it found in that file. And that's how we built the graph of and the plan of what should be recompiled, by comparing APIs that changed, seeing the dependencies from that API, and that gives us a plan of what should be recompiled. Yeah, so going in more detail, looking at stamps, this is what tells us that the A Scala file has changed on a file system, so perhaps it has introduced some breaking changes, so we should recompile that. Because of course, if you don't change any files at all, then nothing should happen, because all the files will have the same bytes, so nothing will happen. Then yeah, the API structure is, we're recording a very simplified version of the code. So we'll just say there's this class A and it has a few methods or some fields inside, but we don't care about the method bodies or what's inside those definitions. We only care about what is publicly visible, basically like what would break compilation if it changed. So yeah, and then we actually collapse all these methods together. So let's say we have 3 overloads of foo, and all we record in the end is just this hash of the combination of foos. Because if you have a source dependency on, all you know is that you called a method foo with some arguments, but you don't know which foo it was, because perhaps in the next time you recompile, you've actually added a new overload of foo, which takes the same number of arguments, but now it's more specific, so you have to choose a different one. So it's only useful to basically say that there exists some foo, and we collapse all the signatures together into this one hash. Yeah, and like they say that if you add a new overload or you change the type of a parameter or you change the result type, then it's going to change that hash. And then you know that you really have to recompile anything that used the foo from A. And then the other side of that is these dependencies. And that really tracks very simple things, just that, if a class inherits from some other class or some class uses some method, and we don't actually care where that name came from, because we have, because of source and for example, there's many different ways you can depend on a name foo. It might be some implicit conversion that gives you this method foo, or maybe you used some global foo and you changed the scope to add a new global that's more specific. So you don't really care where it comes from. You just have to know that you use this foo, because if you add a foo somewhere else, anywhere in the program, then perhaps it might break your code. So we just track that you used foo and don't care where the foo came from. And then the third thing you track is that this class did use specifically the something from that class. So there's a sort of combination of an overlap between using foo and using something from A. So maybe used a.foo, but it's not actually necessary. So yeah, the summary of this is basically that with these simple data structures, this is actually a really good way to efficiently compute the graph of dependencies and make a plan of what to recompile. And that's called the name hashing algorithm. So let's next thing, let's just give a little overview of how to how we gather all this information. This is sort of an X-ray. Imagine this is Zinc. This is just a wrapper around the real Scala compiler, and that's called Scalacenter. And that's made of a bunch of little modules that we call phases. And these each do an atomic transformation on code. So then we have parser, which reads the file and turns it into the internal data structure that the compiler understands. Then we have the typer, which goes through that, what's called an abstract syntax tree, and analyzes it, checks that it's correct, and then annotates types so that nothing has to be recomputed from that point. And then we reach this point called the pickler. And this is the thing that basically, once we've fully type checked the program, then the pickler is going to extract from the program basically the signatures that are necessary to compile against libraries. For example, they all store these tasty files, which is necessary to recompile against them. And what Zinc is doing here is going to add in 2 extra phases, which record both those dependencies and API structures. And they send them back to Zinc through this thing, through this callback, which basically just updates some data structures it knows about. And then eventually when you reach the end of this pipeline, then it's going to write those APIs and dependencies into the analysis. Okay. So another way you can speed up the build that is implemented in Scala build tools such as SBT is that if you, instead of having one big project, you split it up into little projects, then we can actually get some more performance improvements as well. So yeah, like I say, instead of having this one big project, then if you group them up into these modules, then we are again making even more granularity of dependencies between these projects, which gives us more efficient compilation. So to illustrate, let's say we had that web service from the very beginning of the talk, and instead we split up into these separate modules, one with some utilities, the common, and this is shared dependency of the database interaction layer, the authorization layer, and then some models for interaction with users. And then the server brings those all together to create the service that you actually put on the server. And why, if I color coded it this way, it's because everything with the same color is considered like a layer. They're all the same level of dependencies. And what that means is that when we're writing a scheduler that can build your entire project, remember once before we just had 50 files and we sent all those 50 files to the compiler. Well, if we split it up this way, this is what it still looks like if you had a single thread. You run the common first, which was at the top, and then you do the middle layer, one after the other, because we have a single thread, and then the service layer at the bottom. But in a multi-threaded environment, such as most computers these days, if you're building with SBT, for example, then we can schedule all those red projects to run at the same time. And that, of course, saves some time at the end. So the second piece of advice is, yeah, split up your project into smaller projects. And that means that you can save a lot of time building because you can schedule some of these projects to be built in parallel. And one of the things I'm working on right now at the Scalacenter is to make an even better scheduling model for this, which is called a pipelined build. And what that means is like, is it possible to begin compilation of something before we finish the upstream? And yeah, in the Scala world, this has been explored for about six to 10 years at this point, but it's never really been stabilized. And I'm really hoping that we can improve that in the future. So I have a pull request currently, the .e repository, and I hope it could be merged in the next couple of weeks. So that will add support for the so-called pipeline builds for the SBT build tool. But yeah, what is it? So let's say we had, again, this is some project that is being built in a multi-threaded environment. So, but because they depend on each other in this sort of chain where we have C depending on B, which depends on A, then they have to be all scheduled to run sequentially. And this is just a problem because there is a better way to use the CPU's resources by pipelining, that is. So if you turned on pipelining, then actually suddenly we can start the compilation of project B before project A is finished, and then C before project B is finished. And the way this works is because we only need to run the compiler up to the point where we have that pickler phase that writes the signatures. And then at that point, then that's all that is needed to start compiling the project B because it reads those signatures, nothing else. So the project 4 can continue like doing its transformations and lowering to the runtime model, but project B doesn't need to know about that, so it can start earlier. And here's a little experiment I did while compiling the Scala 3 compiler itself. This is basically I've recorded. I did some profiling so I could record the how long it took to run through all the projects that are necessary to build the Scala 3 compiler. And it took about 30 seconds when I fully so-called warm up the compiler because it's on JVM. So you have to JIT compile the compiler over several iterations before it's fully optimized. And without pipelining, it was 30 seconds. And then when I turned on pipelining in my experiment, then we were able to shift these downstream projects starting a lot earlier. So even like 2.5 seconds earlier. But this is a very small project up here, the standard library. So it didn't really save that much time in the end, only about 2 seconds. But for you could imagine that, for example, if this project graph was inverted and we actually had this project at the top as the first thing, then we could actually start things a lot earlier than waiting to the end. And what did I do to the compiler to implement this? Basically, I add a mode where once we reach the end of this pickling phase, then we write the tasty. And as soon as we've written that tasty, then we don't need to care about finishing the rest of the compilation before we tell the build to begin starting the downstream project. And I mean, yeah, so I have some more benchmarks that I did on this computer, which is quite old at this point, but it has 16 gigabytes of RAM and 8 cores, whatever. So there was this big project called Lichess. It's like a free chess server. And building it with the pipelining turned on, it gave like a 25% speed boost. But then it used about 1/3 extra memory to do that because of the increased parallelism. So there's some trade-off. If you have a lot of memory, it's a good option. And in fact, if I had even more memory, it'd probably be a lot quicker because yes, it's quite heavy on the memory running a compiler. And here's some other comparisons with some other projects I did. So yeah, the best one that I found was Scala Dex with 31% improvement to the build time. And if we look at the structure of the project, then it becomes clear why there's such improvement. Is because there's 4 levels of dependencies between the most common and the base. And most of the time, a lot of projects don't have many layers of dependencies, so they don't improve that much. But if you structure your code well, then maybe you can benefit in this way. One project that really doesn't benefit at all is the Guardian newspaper. They have this, their website is built with Scala, but the problem is that they have so many of these tiny little modules in between the common and what's called preview, which I think is the thing that assembles everything together, that when you turn on the pipelining, there's not enough threads to really benefit from the parallelism at all. So sure, when you turn it on, the pink stuff starts before common finishes, but then because of the scheduler is completely starved, then you end up actually finishing common last out of everything, and it doesn't improve the build time at all. So yeah, maybe it works to have a lot of small projects, but you know, sometimes it won't actually improve the speed of your build. And now I'll talk about another thing I did work on before Christmas, which really does feel like a leap ahead. It's something called outline compilation. And this is basically where, imagine we had the full compiler pipeline here. So a lot of this slowness comes from type checking, and then a lot of it comes from this other phase called inlining, which is basically running macros. So this stuff takes a lot of time. And previously with just pipelining turned on, it sort of starts at this point. But the idea with outline is that we run a quicker version of the type checking that skips the bodies of definitions. So we just literally don't even read the bodies of definitions, and that speeds up type checking a lot. But then that means that brings forward the point where you can start the pipelining. So it's a lot quicker to get to pipelining, but then you have to do more work afterwards, because then you have to run the entire compiler again, but in this second portion. But one of the benefits of doing it after we reach that magical pipelining point is that we can instead run that second phase in batch in parallel. So we can split up the source files into several pieces, and then each little bit will be able to still see the entire class buffer definitions that were found in this initial phase. So in theory, this should make a lot more save time because, but it really depends on the scheduler that you have. So here's the experiment I did again with Scala 3 compiling itself. This is without pipelining and without outlining. And then when I turned on pipelining and outlining, then we got this massive, massive speed boost, basically cutting it down by 10 seconds or 1/3. And we can have a little analysis of what's going on here. So really, this Tasty Core project can start almost a whole 4 seconds earlier than before. But then the library does actually take a little bit longer to compile than it did before. But you know, it doesn't really matter because we were able to begin the compiler itself so much earlier, as you see with this gap here. So the biggest project, the compiler itself, begins, you know, so much earlier. And then if you compare this yellow line, that's the type checking. It runs in actually only 2.5 seconds for this outline mode, whereas before it was running up to, what's that, like 10 seconds. So it's so much faster to run this, and then when you run the back end of it in batch, then it really improves the speed. But yeah, this kind of experimental how many batches you want to run, because the JVM needs a lot of threads to, for example, run garbage collection. And if you just fill up all your threads with these batch compilation tasks, then it really slows it down. So I found 3 was the sweet spot for this specific project on my machine. So it's a real kind of debate of like, maybe you can tune it for your CI machine because you know your CI machine has a specific architecture, so you can tune your build specifically for your CI machine to make it really fast. It's kind of an exciting development. So yeah, the raw numbers without any pipelining or outlining, it takes 30 seconds on the fastest warmed up JVM I could get, and 19.5 seconds with all the outline turned on, which is 1.5x speed up, or like, yeah, a whole cutting out 1/3 of the build time. So that's a really nice speed up, I think. And depending on which kind of project you have, there's definitely possibility for way more benefit. And you can obviously, I tried to make it such that the settings are all exposed, so you can really fine-grain tune for each specific project. Yeah, so I also have a pull request with the pipelining, but with the outline compilation. But I think that's going to take a lot more time to refine. But yeah, when the pipelining comes out, I hope people use it. So keep an eye out if you're a fan of Scala 3. And you can try this out on Scala 2 as well. Support has been there since like 2021, I think. So if you know the SBT build tool, there's just this setting called use pipelining, set it to true, and then it works on Scala 2. So yeah, that was kind of that for me. So yeah, does anyone have the questions?
Yeah, we got one question actually here. Thank you very much also for your presentation. It's very interesting to see. I mean, this is a topic I guess you can go on for a lifetime, just scratching off seconds on the, pushing
Yeah,
to the left.
It's maddening.
Yeah, it is exciting. I mean, you can really go into it. Is lowering to JVM bytecode just super fast? The only other compiler I know ends up spending most of its time waiting for LLVM.
Yes, so to compare against like Rust or something, or even Scala native, in comparison, JVM compilation is quite fast because it doesn't do a lot of work of optimization, and it leaves all the optimization up to the runtime of the JVM. So yeah, it is faster in some ways, but people do still complain about compile times with Scala. But yeah, the reason is a lot faster is just because the class file format is more like a simplified version of the program that still looks like code. It's not really that low level.
Okay, interesting. Have you set any goal, like this is what we want to come down in Scala and compiling Scala? Or is it just we're gonna keep on what do you call it, optimize?
So my projects for the year are to one, land that pipelining, hopefully onto do the outline as well. But there's a lot of debate about architecturally what's the best way to do it. I mean, one of the ways that people are figuring out if you got enough money is to host such a so-called build cache, which is where you have like basically if you have a billion line code base, then you actually build all the code, upload it to the internet, and then someone only has to check out a small bit of it and compare against that. And that's another way, but yeah, you need to pay for hosting, I guess. So that's one way to do it. And then there's also like this level of parallelism. It's quite hard. It's a hard problem to do parallelism because there's so much mutability in the compiler that you have to look at other ways of sort of approaching the problem or maybe even re-architecting things. So it's quite difficult. And micro optimization is also hard because you think you fix something in one way and then it ends up like, I don't know, you end up reading memory and invalidating cache a lot more, even though you don't allocate on the heap as much. I don't know. There's a lot of tricky things to figure out that. But my plan is to probably spend 30% of the year at least on this.
Okay, so there you go. We'll expect more optimization than from the build times and everything. Yep. Thank you very much, Jamie, for your presentation. And now, for all the people that are still here and live with us, we'll head over to the Discord server and chat even more with Jamie and the other people. And if you have more elaborated questions, please join there. And I hope Jamie can answer all the tricky questions you have about optimization and compilers. I'll also have some more questions to Jamie actually, but I'll ask them on the Discord server. So with that, thank you very much, everybody, for tonight or today or wherever you are in the world watching right now. So have a nice and pleasant evening or day, and see you next time. Bye.